Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're very, very happy to have Daniel Witch here. So most of us know Daniel. He's been an intern with us, and he's from NYU, supervised by Evgeny Dodis. And he's done really wonderful work in crypto. Some of his really beautiful stuff has to do with Leaky and tamper-resilient cryptography, which is what he's going to talk about today.
All right, thanks, Yael. So I'll be talking about cryptography with weak, noisy, leaky, and tampered keys. Essentially, all kinds of bad things can happen to your key. Can you still do crypto? So we all know that cryptography requires secret keys, because if you can decrypt messages intended for you and you don't have any secrets, then everyone else could decrypt as well. That would be bad. So we need secret keys. And the way we usually think about these is that when we design a scheme, we specify how the keys are chosen, what the distribution is, and how they are used. So the scheme tells you exactly what you should do with the key. And essentially, so everything's under our control, and the attacker has no other access, no other way of getting information about the key other than what we specify when we design the scheme, other than kind of interacting with the scheme. And so this talk is about kind of scenarios where that might not be the case. So for example, you might want to use a password or biometric as a secret key, and we can't tell you how to choose your biometric. You kind of have to use what you are given. Or you can even, yeah, maybe eventually. You might even choose your secret key really honestly and as we specify, but then when you use the secret key, there can be some leakage, or the attacker can get some extra information. This is through things like side channel attacks. I'll explain what that is later. And lastly, at least if I have time, I'll talk also about potential of keys getting modified or tampered, again, beyond what you want or what you have control over. And so the main question for this talk is, can we construct crypto systems that remain secure even with these kind of imperfect keys, where we don't have full control over the distribution or what the attacker can learn? And so the focus on this talk, the task I want to focus on is just secure communication. So this is kind of the bread and butter of cryptography. So we have a user, Alice, and she just wants to communicate securely with another user, Bob, over a public and completely insecure channel that's controlled by some attacker, Eve. And the two properties we want are, first of all, privacy. So even if Eve observes the communication over this channel, she shouldn't learn anything about the message. And second of all, authentication. So even if Eve is active and tries to modify the contents of the channel, she shouldn't be able to get Bob to accept the message that didn't actually come from Alice. So she can't insert or modify the messages over the channel. So those are the two things we want. And so the first question we're going to ask is, can we actually get information-theoretic security using a shared weak key? Okay, so information-theoretic security is the kind of security that Shannon studied in the 40s. It means that security actually holds statistically, even if the attacker can run in exponential time, is all-powerful in terms of computation, still security should hold. And with information-theoretic security, the best we can hope for is that kind of with one use of the key, Alice can only send a single short message to Bob, and that's what we're going to look at. And the setting we're in is that Alice and Bob start out by sharing what I'll call a weakly random key. So what that means for this talk is that we don't know what the distribution of the key is. Well, in fact, we can kind of assume it's adversarial. The attacker chooses the distribution that this initial secret that Alice and Bob start with comes from. So he doesn't choose the secret itself, he chooses the distribution. The only guaranteed property we have on this distribution is that it should have some sufficient level of entropy. So it should be hard to predict a sample from this distribution with good probability. So that seems kind of necessary, otherwise it's not really secret if you can predict it. And so hopefully this should model things like passwords or biometrics, where we just don't know too much about the distribution that these comes from, so we might as well assume that it's adversarial, because we really don't know much else about it. It should also model things like partial leak keys. So if you start with a uniformly random key, and then the attacker can learn some information about it, even information that the attacker chooses what to learn. as long as the amount is not too large, let's say the attacker learns like 3/4 of the key, then conditioned on the leaked information, the key still has some entropy, but the distribution is kind of chosen by the attacker. Depends on the leakage. So the first question we can ask is there just a general method that lets us convert a weak key into a strong, kind of uniformly random cryptographic key? Can we just do something generic like that? And there's actually a tool that's designed for this purpose that lets us do this. It's called a randomness extractor, defined by Nissan and Zuckerman in '96. And this is a function that takes a weak secret W and somehow extracts out a uniformly random key. So that's great, except there's a catch. The catch is that in order to do this, the extractor also needs some additional uniformly random seed. So you can think of it as some helper data that you need in order to extract out the uniform value. And so the good news is that the seed can be made public, so you can tell everyone what the seed is. And the property you get is that no matter what distribution, what weak distribution W comes from, the extracted key K looks uniformly random. It looks like a uniformly random value, even given the seed, even conditioned on seeing the seed. Sometimes also called strong randomness extractor, but that's all we'll consider here. And so these extractors have a lot of uses on complexity theory and cryptography, and here's kind of one use. They give us one solution to this problem kind of right away. And the solution is that when we design the scheme, we just choose a seed X at the beginning of time. So maybe Microsoft wants to design a scheme and says, everyone, you should use the seed X. That's what we chose, and that's the seed for everyone. And we kind of hard-code it into all protocols. So whenever somebody writes a protocol, they'll do pound define, seed equals, and they'll all use the same seed. And then if you want to use a weak secret for cryptography, the first thing you do is just extract out a uniformly random key out of it and then use that. Then do whatever you would do with a uniformly random key. So this kind of completely gets around weak secrets. There's two problems with this solution. So the first problem is that the users would need to trust that the seed X was actually chosen honestly by Microsoft, right? So you have to trust that Microsoft chose it uniformly at random. So some people might not like to do that. They want just a single scheme that we all know works, not kind of some randomly chosen scheme. The second problem is that this only works if the distribution that the secret W comes from cannot depend on the seed X. So in some sense, the idea here is that first the attacker chooses the distribution, then Microsoft chooses the seed, and then you choose a sample from this distribution. And that might be okay for passwords or biometrics, because that's kind of a fixed distribution probably. It's not like people are adaptively choosing their biometric depending on some seed. But it's bad for things like leakage, because if the attacker can choose what to leak, then the leakage can depend on the seed of the extractor itself, so the attacker can actually target it kind of at that particular seed, and all bets are off. If you try to do this, then the extracted randomness might not be actually uniform. So here's another solution that kind of seems to solve this problem or get around these problems. So instead of having the seed hard-coded and having kind of one seed for everyone, why don't we let Alice choose the seed? So she first chooses the seed, and then she extracts out randomness at her end. She sends it over to Bob, and he uses it to extract out randomness on his end. So okay, this actually kind of works if you care about privacy. Alice then uses this key to encrypt a message to Bob, and Eve is just passively observing the communication. Then this works because even conditioned on seeing the seed, the extracted key looks uniformly random. So that's good. The problem is that this doesn't work if Eve is active and can modify things over the channel. So for authentication, this doesn't work. The problem is that Eve can just modify the seed and give Bob a completely different incorrect seed and cause Bob to extract some bad key K prime. And all bets are off about K prime. It's possible that Eve can even choose this bad seed in such a way that she completely knows K prime. Okay, so she can get Bob to extract the completely bad key, and then that's bad. She can authenticate messages to Bob on Alice's behalf under this bad key and convince Bob that they came from Alice. So this completely breaks authentication.
And also secrecy, then Bob needs to send something.
Right. Yeah. I'm thinking for now that Alice is sending the message to Bob. So if Alice is using the key to send a message to Bob, then secrecy is okay. Yeah, if it went the other way, you're right, it would also break secrecy. So the question is, so this particular protocol doesn't work, but is there some other way? Can you authenticate a message to another person if you only have a shared weak key? So is there some protocol for doing that? And so in a joint work with Dotis, we actually showed that this cannot generically be done in one round of communication. So if Alice just wants to send one message to Bob and convince him that kind of this message came from her, you cannot do it. You cannot have a protocol like this. So this is something you can do if you have a uniformly random key. In fact, just using pairwise independent hash function, this works. But with weak keys, it actually cannot be done. On the other hand, we show actually that there's a two-round protocol. So just a protocol where Bob first sends some challenge to Alice, and then Alice sends something to Bob and convinces him, authenticates a message to him in the second round. Okay, and so I'll show you a little bit about this two-round protocol. I just wanted to mention that prior to this, actually, people had protocols for how to do this, but with many rounds of communication. So actually, the number of rounds wasn't constant. It was proportional to the level of security you wanted. In practice, something like 100 or hundreds of rounds. So I think the main thing about the protocol that I'll present is that it's conceptually a lot simpler. It has a really nice structure and leads to like a very simple question about extractors. So here's the main idea, and the main idea is to just reverse things. So actually have Bob choose the seed X and send it over to Alice in the first round, and then Alice and Bob use the seed to extract out randomness from their joint weak secret. And then in the second round, Alice uses some standard method for authenticating a message with a uniformly random key. Okay, so we just really reverse the way things worked here. And why is this better, or why would this make sense? Why is this somehow better for active attacks? So let's assume that Eve is active and she actually modifies the seed in the first round. Okay, so she's going to send the wrong seed. So now kind of all bets are off about the randomness that Alice extracts. Right? This could be bad, the key that Alice uses. But Bob still has the right key, and he's the one that checks whether the authentication is correct or incorrect. So somehow, if Eve wants to forge in the second round, she needs to authenticate a message under the right key. So that's good. There's still a problem that Alice's key, K prime, might be bad. So it's not a problem if it's a key that, let's say, the attacker knows. Because she starts to forge under the original key, which is strong, and so just seeing some information about a key that she knows doesn't really help her. Well, the problem here is if Alice's key K prime is actually in some bad sense related to the key K. So somehow Alice is getting, if somehow Eve is getting Alice to use an incorrect key to do the authentication, which might be related to the correct one. And using that, she can learn some extra information that lets her forge messages or break the protocol in the second round. In some sense, you can think of this as an attack, actually, where Eve can actually tamper with Alice's key K prime by somehow modifying the seed. So I'll talk about tampering attacks later, but somehow this, even though it's not real, the goal isn't tampering, or it's not like Eve is tampering Alice's key directly, somehow it translates into a tampering attack. Yeah?
So you're going to get authentication, but there's no privacy anymore?
For now, I'm just looking at doing the question of authentication. Once you do that, it's actually easy to combine it to get both privacy and authentication at the same time. In 2 rounds, yeah. Yeah, the idea is you authenticate and use seed in the second round, and then use them. There's some complications with doing that because there are, you are using the same key for many things. You have to be a. Why? It's a completely different key for the privacy. Yeah. So, yeah, you have to. Well, things aren't completely different because they all come from the same source. But it does essentially work, right? Because if you extract out 2 different keys for W, they're not. But yeah, it is pretty easy to stick it on top. Yeah, I think your intuition works.
Sorry, did you say 2 additional rounds? Or?
No. Just in 2 rounds like that. So yeah, to do that, just in the second round, the message that you authenticate is just a new seed for an extractor, and then you can use that key to do everything. So yeah, but I just want to focus on authentication. It's really the hard part here. Okay, so yeah, so the problem is that, you know, by modifying the seed, Eve gets to tamper the key K prime that Alice uses. And unless we analyze some properties of the extractor, we just have no idea what this tampering will look like or what kind of tampering attack this translates into. So on a high level, the problem is that if you see a random seed X for an extractor and can choose a related seed X prime, somehow based on X, then the extracted values using the seed X and X prime are somehow related to each other in some bad sense that we don't know much about. And so the main question that we ask ourselves is, are there extractors for which we can say something interesting about this relationship, for which we can somehow analyze how K and K prime are related to each other? So essentially say that the tampering attack is not too bad. It's limited what Eve can do. We call these non-malleable extractors, and we have we actually showed have two results. So first result says actually there's such a thing as a fully non-malleable extractor. Even if you see the seed X and choose an arbitrarily related seed X prime, the randomness that you extract at X prime is completely unrelated to the randomness you would extract at X. So even if you see it, you don't learn anything about what you should have extracted. So
Even given K prime.
exactly, yeah, K looks uniform even given K prime. And that's great. If you plug that into the protocol on the last slide, you're done. You get security because by modifying the seed, the attacker doesn't get anything.
So that should be straightforward given that you can just pick random functions at this stage, right?
But the function is known, right? So it's like, it's not totally, you mean random function for the extractor?
Yeah, for each seed, it's a different random.
Yeah, that's actually that's our proof. We have a non-constructive proof.
But you're saying that it's not easy to prove that that's good because the randomness is known.
Yeah, it's not completely true, but follows the same kind of proof that standard extractors exist. You just have to analyze this extra malleability property. But yeah, what we end up showing is that just a random function has this property. But of course, a random function isn't kind of efficient. We don't have efficient description, so it's a non-constructive proof. We don't actually have an instantiation. So instead, we show a slightly weaker property. We call it somewhat non-malleable. And I don't want to get too much into details, but essentially, we show that the relationship between K and K prime is somehow limited. And this property turns out to be sufficient for the protocol on the last slide. So it lets us solve that problem. But I think it's still an interesting question if fully non-malleable extractors exist. And I know people are working on it, so I'm hoping that there will be a construction soon.
How do you measure relationship, like information theoretically?
Or? So it depends on what the somewhat is or so in the fully there's no relationship. So even if you see, in the somewhat it's like a complicated thing that somehow the extracted randomness is somehow divided into blocks, and you can say like the first block of the modified key is unrelated to the second block of the original or something like that. So it becomes not a super nice relationship, but something that you can reason about and then can build an authentication protocol on top of it. Can actually use, you can reason somehow about this relationship and build things from it.
Do you use the non-extractors for this, or just new analysis of some non-extractors?
No, we use kind of known extractors in a somewhat black box sense to build another kind of extractor, but it's not any known extractor or we don't have any nice analysis for how known extractors behave under these modification attacks. We have to construct something new.
And the consequence of the somewhat is that you lose some of the entropy?
The consequence of the somewhat is that you have to actually build a more complicated authentication protocol because your authentication, there is still some relationship between the keys, so you have to build an authentication protocol that's secure. Kind of this second round authentication scheme that you use has to be secure even against some limited modification of K prime, right? So you have to do something more complicated there. You can't just use one straight up. But the end result actually ends up being, you lose a little bit in the entropy. So you need to assume the weak secret starts up with more entropy than you get at the end. That's the end result.
Not much more, right? You lose very little.
Yeah, it's depending on the security parameter. So nothing related to the size of the secret or anything. Just depends on the level of security you want. Yeah. Okay, and so So let's actually look at an application of this. So let's say you actually wanted to use this with biometrics. Let's imagine a scenario where Alice has some biometric, like let's say fingerprint, and initially she registers with some, you can think of it as like some sort of a service Bob. So she gives him an initial scan of this biometric, and he keeps that. And later she wants to communicate with Bob, she'll take a fresh scan of her biometric. The problem, so can we use the protocol straight out? Well, the problem is that usually if you take scans of a biometric, they're not exactly the same. There's some errors. So Alice's second scan W prime will not be exactly the same as W. And there's actually an idea for how to handle this, which is that Bob sent some sort of also a sketch of his secret W that lets Alice correct out the errors. And you can actually do this in some clever way that you send a sketch that lets Alice correct out errors without revealing too much information about W. So that's actually kind of clever schemes that people have thought about for how to do this. And again, this like right away lets you get passive security. But if you care about active attacks, then now Eve gets one more chance to modify things. She can now modify the sketch as well. So you have to also handle the fact that Eve can modify the seed and the sketch together. It kind of gives her more tampering of the key K prime that Alice extracts. And in fact, the kind of the way we handled this was a fairly general method for handling linearly tampered keys. The main idea is that most of these sketches are actually linear. So when you try to use an incorrect sketch, it just translates into a very simple kind of tampering attack where the key K prime is offset by some known constant. And this, we actually kind of came up with pretty general ways of handling this that seem to have a lot of other uses. So they also will be useful when I actually talk about real tampering attacks later on. I think actually, so this is kind of for biometrics. I think this could be useful for in a lot of other applications. So one thing I was thinking about is maybe if you wanted to establish like a shared key between two cell phones, you could take them together and shake them and just take the motion data of the cell phones. And you know, this motion data probably has a lot of entropy, and it's probably not exactly the same, but it's going to be correlated. And so that's something you could probably use these types of techniques to correct out the errors and establish a real key out of it.
Distance between different.
Yeah, so I didn't say much about the distance. It is in some metric, and we do assume some distance. Generally, like what people do is they take, let's say, biometric scan, and they extract out some features. So they create a feature vector. And then if you take two close readings, they are actually close over Hamming distance. So you can even use codes over Hamming distance, and they're meaningful in the sense of biometrics. Yeah, that's a good question. Okay, so I want to move on to kind of the next topic, which is, so now we saw how to do information-theoretic symmetric key cryptography. Can we do public key cryptography with weak or leaky keys? And here I'll actually focus more on the case of leakage, although the techniques usually work for a key that starts out weakly random as well. So the scenario here is that we want to have an encryption scheme which is secure even if the attacker can leak some partial information about the secret key. So we assume the secret key and the public key are chosen kind of correctly as specified, but then the attacker can choose any kind of information about the secret key to leak as long as the size of the information or the size of the leakage is not too large. Let's say less than 90% of the key can leak. And so this is an area that there's been a lot of work in the past 2 years. I think so actually it started with the work of Akavia, Goldwasser, and Mike Contenathan. They did encryption schemes, and then we showed how to do signature schemes in this setting. And then people have studied all kinds of different, how to do it under different assumptions and kind of different types of schemes and some variants of these models. And I think these are interesting, but it gets a little technical. So I'm not actually going to tell you too much about the construction of these schemes. Instead, I want to focus on like kind of an application or variant of this model that I think is interesting. And so the application is, the main question for this application is security necessarily lost if a machine that stores cryptographic key is infected with a virus? Can you get any kind of security if your machine has a virus on it? And so the model is that we have some computer that stores a secret key for a cryptographic scheme. And we have a remote attacker somewhere in, I don't know, Belarus or somewhere far away that can just download arbitrary information from this compromised machine. So it can download whatever it wants. can you kind of maintain any kind of security in this setting? And so I think an idea that's interesting for how to do this is to just make the secret key huge. So make your secret keys like 100 gigabytes. And then try to use a scheme that's secure even if 90% of the key leaks. So here's the idea for why that might be useful. So in order for the attacker to break security, right, to actually break the scheme, the attacker would need to download at least 90 gigabytes worth of information. And that might be kind of hard to do because maybe bandwidth is too slow, or it would cost too much to download 90 gigabytes, especially if you wanted to do this attack on a very large scale. You have to download 90 gigabytes from each compromised machine. Or it might be just easier to detect leaking 90 gigabytes worth of data. Okay? And on the other hand, the storage cost to the user for storing 100 gigabytes is really not that large. It's like $5, using like Newegg estimates. But okay, so there's a problem. The problem is that if you try to use kind of a standard scheme, you'd also get giant computation times and public keys and all kinds of other things. So you definitely can't expect the user to do some complicated computation over a 100 gigabyte key to sign a message. That's completely unreasonable. So what we'd really like is to have a scheme where the secret key can grow. We can make the secret key 100 gigabytes, but only the secret key grows, and everything else stays efficient. So the public key stays small, kind of the same size as normal crypto schemes, and the computation times remain small. So for example, if you want to sign a message, you can't even read the entire secret key to do that. And so that's something we looked at for. Yeah, so for signatures, it's like signing the message and verifying the message. For encryption schemes, it would be decrypting the message and encrypting it, yeah. And so that's the idea. Can we have these efficient schemes with huge keys? And so I want to tell you a little bit about an idea for how to actually construct those, just kind of a very high-level idea. And that is, let's say we start, I'll do it for signatures for now. It's easier to think about. But let's say we start with a signature scheme that kind of has normal small keys, depending on how much security you want to get, that are resilient to 90% of leakage. Can you construct a scheme with a much bigger key that's resilient to kind of this more leakage on an absolute scale, let's say same percentage? And here's an idea. Let's just take many copies of the scheme. So choose many independent secret keys and public keys, and let Alice store all of the secret keys. So 100,000 secret keys, whatever gets you to 100 gigabytes. I don't know how many that is. And Alice will store this whole database of secret keys. For now, Bob will actually also store a database of public keys. So we'll solve that later. Now the public key will be huge. But this is just the first step. And then in order to sign, Alice will just create a signature under each one of the keys. So here the computation time is also large. We'll solve that later also. But the question is, does this scheme, just taking many copies of a signature scheme, does that actually tolerate more leakage on an absolute sense? Does it tolerate 90% leakage on the combined secret key, if each one is secure for 90% on the small one? And the intuition says yes, because if you leak less than 90% of the big secret key, there should be at least one little secret key on which you leak less than 90%. You have less than 90% information. And so if the attacker can't sign under that one, she can't sign under the whole secret key, right? Because she has to sign. She has to sign under each one. So the signature here is to sign under each key. It's not efficient yet. We'll solve that in a second. But here, the first idea is just, can we get a scheme with more leakage? Forget about efficiency. Can we get a scheme with bigger keys and more leakage? If we have a scheme with small keys and some small amount of leakage. And so the intuition says that this should work. But interestingly, if you actually start doing the proof, it doesn't seem to go through, because there's just no natural way to convert leakage on the big combined key into leakage on each of the little keys. So somehow the reduction doesn't seem to go through. And so what we ended up showing is that it actually holds for some specific schemes. And we thought that there should be counterexamples, but we didn't actually know how to do them. And people really like this problem. So recently there's been 2 works that show counterexamples to this lemma. So kind of they construct a small scheme that's secure against 90% leakage, but if you take many independent copies of the scheme, then you can break it with much less leakage than just multiplying it out.
Saying that exactly 90% of the bits are leaked, or no, some function?
Some complicated function, yeah. Leakage is a complicated function here. It's not just bits. If it's bits, then this works, yeah. Yeah, the point is that leakage can be an arbitrary kind of related information about the key. So, the virus can do some pre-computation and leak whatever it wants.
There's some sort of well-defined sense in which you can leak, say, 95% of each of the small keys, but only 90% of them collectively. I mean, I'm willing to believe that there's something that goes wrong in the proof, but I'm really curious.
Okay, the intuition is that there's some sense in which when you leak at 90% on the combined key, so you can kind of adaptively choose the leakage on the keys based on each other. It's not equivalent to leaking just individually, 90% on each key, or even there's no sense in which you can say that there's a single key on which less than 90% was leaked. I guess that's really the main intuition. You can somehow real adaptively. The leakage is kind of a global function, I guess, on all the keys together, and that really helps you out.
So the counterexample says that with some positive probability you will be able to forge the signature.
Yeah.
Always.
I think even there it's always actually. Yeah. So there's some. So I think one of the counterexamples is like even if if you take n copies, you expect the leakage to amplify n times the absolute amount of leakage that you can tolerate, and it says that you can leak like n over 2 times as much leakage and break the scheme always. So yeah, I think there's going to be there's also I think counterexamples where it really doesn't grow almost at all beyond beyond some threshold. It just doesn't. If you keep taking more scheme, it won't. The amount of leakage you can tolerate it won't grow.
Is there any connection between all this and Ray-Ban scheme for broadcasting giant keys from satellites?
There is, yeah. So that's called the bounded storage model. People call this the bounded retrieval model. So it is similar in that sense. There's maybe like in how people. So there's a lot of similarity in the techniques, especially, but in terms of the ideas, I guess there you think people have actually small storage, but there's somehow this huge key in the sky. Here you think people have large storage, but there's some leakage on it. Yeah. Limited communication. So it's kind of the opposite conceptually, but the techniques, there's some relationship in techniques. Actually, this relationship will kind of be in this part more. So this scheme is still not efficient, right? I still, the public key is huge, the computation times are huge, so I still didn't tell you how to do that. And it turns out that it's pretty easy to make the public key small. So this can be done generically using certificates, so you kind of sign all the public keys under some other public key. That's not too complicated to just reduce the public key size. But still you have to sign under each one of the secret keys. And so to get rid of that, actually, the main idea, and this is something that people did in the bounded storage model as well, is...
So I sign all these guys with a single key. How do I communicate them?
Yeah, in the signature. So you sign all of the secret keys with kind of a big master public key or something. And then when Alice is asked to sign a message, she says, "Oh, this is my signature under public key 1 in position 1, and here's the public key in position 1, and a certificate that this is the right public key for position 1."
So the signature is going to be huge, but it was huge already.
Well, not huge. I mean, just as a small certificate.
No, because it's signed under all these.
Oh yeah. So that's the second step, right?
Doubled or tripled it or something like that.
Yeah. So right now I didn't make it much more huge, but it's huge just as it was to begin with. And now to reduce the size, the main idea is that you don't sign under all the keys. In fact, Bob chooses some random subset of them. And at least on an intuitive scale, he should hit some subset of the keys that you didn't learn too much on. But again, the intuition kind of doesn't break down generically. But for specific schemes, this actually does work. So that's what we ended up showing. So some of these specific schemes, the analysis is very information theoretic, and then you can kind of information theoretically this stuff works, and so you can show that it works for them.
Isn't this basically the same thing that Ray-Ban was doing? You get all this, you have bounded storage, you get all this stuff, you do random sampling.
Similar. He wasn't doing public key schemes, right? He was doing stuff that's unconditionally secure. So it turns out like the analysis with public keys is complete. So somehow information theoretically, it's pretty clear that this stuff works. When you have computation assumptions, you have to do reductions, you run into exactly the types of problems that things don't generically work.
So in particular things, you know that they don't work generically.
Yeah, you have
So if
counterexamples.
there's something wrong with information theoretic intuition, you have to apply special schemes to.
Right. And it turns out that similar techniques, kind of I did in terms of signatures, you can use similar techniques for encryption. You can't encrypt the same message under each key. That's actually bad. You instead encrypt like a share of the message under different keys. But kind of the same main idea. Okay. So I'm going to switch topics once again a little bit. And next question is, can we do cryptography with essentially under side channel attacks? And what you'll see, it'll translate to something called continual leakage on the secret key. So here's the main idea. Usually when we think, when we think in theory about what a cryptographic algorithm is, it's just there's some algorithm, there's secret keys in this algorithm, and the attacker can give it inputs and gets outputs, and that's all the attacker sees. And then when you actually try to implement this, you'll put this algorithm on a physical device. Things go a little bit wrong because there's kind of more there. So for example, you could take the time, measure the time that the device needs to run the algorithm. And that can reveal some information about the internals. You could try to measure the electricity that it uses, or even the sound that it emits, or all kinds of radiation. So essentially, just on a high level, the problem is these things are called side channel attacks, and the problem is that there's some observable physical properties of the device that can reveal information or partial information about what's going on the inside. Okay, and so fine. So side channel attack is some partial leakage of the internals of the computation. We just told you, I just told you that we can handle leakage. So are we done? Well, no, there's a problem. It's partial leakage per use of the scheme. Each time you kind of call the algorithm, there's leakage. You call it on a different input, there's more leakage. And so eventually, if you kind of keep using the scheme and leaking a little bit about what's going on, you can leak the entire key. So that's bad. Okay, but that's unless maybe the right idea here is to actually, each time the scheme does something, it should also update its internal key. Okay, and then maybe with these updates, if you leak on the different, you're kind of leaking on what's going on in the inside, but the key isn't consistently the same. So it's always a different key. You won't actually be able to somehow combine the leakage to actually do something useful. So that's the main idea here. And so that's something we study, and I joined work with Dodis and Harlembiev and Adriana Lopez-Alt. And we introduced kind of a new model. There's also been a lot of preceding work, which I'm ignoring, but a new model where the secret keys can be, we have a scheme, a public key scheme, let's say a signature scheme, where the secret key can just be updated at any point in time. So the scheme can just update its secret key in some meaningful way. And when this update happens, it doesn't really affect how the scheme works. So the public key stays the same. The signatures it produces are still the same as before. They kind of verify under the same public key. So nothing really changes from the point of view of functionality. Just the key somehow looks different. Okay? And the idea is that the attacker can get partial information on each, partial leakage on each key. So at any point in time can get partial information about the state of the system. But then the state gets refreshed, and this keeps happening. So let me actually illustrate it. Just I think you'll see what I'm talking about. So initially, the device stores some initial secret key, and the attacker, let's say there's a signature scheme, so the attacker gives it a message, and the device outputs a signature. And as this is happening, the attacker gets some partial information, so this like broken version of the key, gets some partial information about the key. And then, let's say the key at the end of the signature, the key is updated. The attacker gives the scheme a new message, and the scheme produces a signature, gets some leakage on this updated key. And this kind of keeps happening. So he keeps getting leakage on each of the, in each period, kind of on the state of the device. And this can go on as however long you want. There's no bound for kind of how many uses of the scheme the attacker gets. There's only a bound on the amount of leakage you can get at each use. And so eventually, you can try to combine the leakage on these various keys, and the main property here is that you shouldn't be able to combine them in a meaningful way to be able to forge a signature of a new message. So you shouldn't be able to produce a signature on anything you haven't seen yet.
The keys are also evolving, right? So I could try to come up with a thing saying, look, after a little while, this is what the key will be, and this is what.
So the idea is you don't know the randomness that's going to be. The evolving is actually randomized, and you don't know the randomness that's going to be used in the future evolutions.
So does it also restrict the space in which the public keys will come from? Can I just claim that as an eavesdropper, can I claim, oh, there was this randomness which led to the following key, and now...
Sorry, I'm so sorry.
I mean, I'm trying to... oh, I see. So the public key has been sort of fixed throughout.
Yeah, the public key is fixed throughout. Everyone knows the public key, and each of the secret keys is kind of a good secret key. It works, right? It's for the same public key. But somehow, yeah, so at the time, when you're leaking at any given point in time, when you're leaking about the state of the device, you don't know what the state is going to be in the next time period because there's some fresh randomness coming in.
That's not the issue here. The issue is you're saying, in spite of all this leakage from all these different secret keys, I still can't make a new any secret key that matches that public key.
So what Madhu was maybe saying, or I don't know, but if the updates, that's exactly what I'm saying, but if the updates were deterministic, then it would fail, at least with this general model of leakage where you can leak anything you want about the key. Because you could always...
The issue is not just that I can't predict the future state of the device,
right.
I can't make any secret key.
Yeah, or actually even a signature, not just you win not only if you make a valid secret key, you win if you actually forge a signature of a new message.
Right.
So even more...
You might assume the only way to forge a signature is to get a valid secret key.
Right. So yeah, it's a stronger...
There are lots of these valid secret keys.
Right. Yeah, there's lots of valid secret keys, and you get leakage on each one, but you can't combine it in a meaningful way. That's the main idea. And so this is something. So we in this work we showed how to do signatures and some key agreement and some other related tasks in this kind of a model. And there's been a lot of exciting work in this area just in the past year. So actually, concurrently with our work, there was a work by Zvika Brakersky, who's an intern here in the Alkali, and others. And there's been that did encryption schemes also. So there's more schemes now. There's kind of stronger properties, how much you can leak on the various updates and things like that. So I think this model is evolving, and there's a lot of exciting work here. And there's much more to do. So I actually want to mention two things. So one thing that I think would be really interesting is so far people have really analyzed how much leakage the scheme can tolerate. But they haven't analyzed at all how much leakage the scheme actually generates. So I think what you need in practice is that the scheme needs to tolerate more leakage than it actually generates when you run the signing algorithm. So yeah, so that's one of the problems. People didn't really know how to do this because we don't know how much leakage or what kind of leakage is available. But I think a reasonable model would be to say that the leakage somehow scales with complexity. So if your scheme is very complex, and I don't know exactly what measure of complexity to use here, but somehow if your scheme makes 200 passes over the key, reads it many times, and does something complicated, it should leak more. And people kind of have ignored that issue. So I think the solutions actually often make more complex schemes, and then if the scheme actually leaks, if complexity leaks, if the more complexity you have, the more leakage there is, then we might actually be making things less secure. So that would be bad. I think that's an important question to tackle. And the other question I think would be really interesting. So far, people have really thought about this for some specific crypto systems. But what would be really nice is just to take any computation, anything you want to do, let's say a complicated voting machine or something like that, and make it secure against leakage. I'm not sure exactly if in this model you might kind of think of different models of leakage or things like that. But I think that's, and people are working on this so far. They have some solutions with secure hardware or some restricted models. But I think this is also an exciting area to work on. And I don't know how much time I have. So there's one more topic I can talk about. Oh, okay. All right. So the last question that I want to ask is, can we protect secrets against tampering attacks? What if the attacker can actually modify the state of the system? And let me kind of start with an example. So let's say we have this attacker Eve, and again, we have this signature token. So she gets a signature token that has a secret key in it. But this time, it'll do something a little different. It also has an ID. So it has her ID equals Eve. And each time she gives a message, the signature token appends Eve's ID. So it says, OK, this is a message with Eve, and signs it. And what Eve really wants to do is she wants to sign something that says, that corresponds to a different user. So you can think of there's a lot of users that all are getting these signature tokens with the same secret key, but different IDs. Okay? And so Eve has her token that says Eve. She wants to sign something under a different user. How can she forge? Well, if all she has is really access to the device, she can really just give messages and see signatures, then there's nothing she can do. This is actually secure, right? That just follows from the property of signature. She can't forge under a different user. And so one thing she could do is do side channel attacks. And then if you use the signature schemes we talked about from the last section, maybe that offers some protection. So that's kind of the main idea there. But here's another type of attack. Maybe she could try to tamper with the device and just kind of like change the last letter, with some powerful laser from an E to an A. So now the scheme stores, ID equals EVA, and just by using the device correctly, feeding it a message, she can then get a signature for a different user. So this is a tampering attack. She's actually modifying. The idea is that Eve can maybe modify, even in some pretty simple or unsophisticated way, the state of the device, so that using the device afterwards does bad things. That's the main idea here. And actually, there's just a really nice work by Bonnet, Demian, and Lipn that showed that if these signatures are RSA signatures, then just by introducing random faults while the signature is being computed and then seeing the signature at the end, you can actually factor the RSA modulus. You can completely break the scheme. So these attacks, you might even like put the device in a microwave or something and get some random errors, and actually that would let you break things.
You need to control the errors so that there are few, or you don't even care?
Yeah, no, it's important. It's few random kind of faults. Yeah, if you just override it with random stuff, you're not going to get anything useful.
The game here is not what you said. It's not to change Eve to Eva. It's to find out what the signing key is.
Well, either one. The game is to forge a signature under a different user. And so there's two methods in which you can do that. Two tampering attacks. I wanted to give two examples. So one is...
No, let me just clarify. I mean, the game, in the sense, what counts as a break is if you get the secret key or you manage to forge something on the original key. And
so the primitives
are that you can get to change your name from Eve to Eva and so on in trying to do that, right?
Yeah, so the first result, you don't get the secret key, but you get a signature under different users. That's bad. I want to prevent that as well. The next result, you actually get even the secret key. So it's maybe even a worse attack. But
seems like the consequences might consider to be worse.
Yeah, of course.
You might consider the attack to be easier also.
Yeah, of course. Yeah, you're right. So, the first attack would kind of work for any signature scheme. So I guess what the first attack shows is it's not necessarily enough to just secure the signature scheme. You have to secure the whole thing. So I think that's the main idea. And so here's kind of an idea of a solution. It's pretty imperfect, but the main idea is to store the actual state of the device in some encoded form. So as a code word. And then each time the device is run, it actually decodes it and then runs the actual computation. And so we'll assume the tampering kind of only happens in the static state, kind of before the device executes. So maybe it's easier to tamper with the long-term memory than like while the device is actually computing. So we'll only consider actually tampering on the code word itself. And also it leads to a nice theory question about coding schemes. So that's always an important thing. But the idea here is that so a tampering attack is really modeled as some family of functions where the functions map code words to code words in some weird way. So if originally the device stores the code word C, the attacker can kind of choose some function in this family and apply it to the code word, and the device stores f of C. And so maybe to write it even more as kind of a standard coding problem, here you can think of it as a channel. So we have a source message, it's encoded, there's a code word, and then the channel applies some function from a family to the code word, gets a tampered code word, and then that's decoded. Okay, so this is kind of, you can think of tampering as a noisy channel, or some sort of a channel. And so there's two questions we have to ask. What does it actually mean to protect against tampering attacks? What are the properties that we want of this coding scheme? And what type of tampering attacks or what families of attacks can you protect against? And so the first thing is, well, maybe what it means to protect against tampering attacks is kind of the standard error correction or detection that actually when you decode, you'll figure out if errors were introduced or can maybe even correct them out. Probably correcting out isn't needed, so detection might be enough. But I want to say that even actually detection is already too strong of a property. And because it's too strong, you can only achieve this for kind of fairly limited classes of tampering attacks. So for example, think of like tampering allows you to just override the code word with a completely arbitrary value that you choose yourself. But it's independent of what the code word was originally. So you can kind of zero out the device or just completely change it. Then you can always put in some valid code word of your choice, so that won't be detected. You can't achieve detection for this type of fairly simple tampering attacks. So, and on the other hand, it's not really a bad attack. It doesn't make the card do anything that you couldn't do yourself to begin with. So it's not going to let you do anything useful. So in a joint work with Zimbowski and Pietrzak, we kind of introduced this new notion of kind of code security, which we call non-malleability. And the idea is that if you tamper with the code word, then the message that's stored in the tampered code word should just either be the same as the original or unrelated to the original. So you can't kind of cause the device to do something related to what it was supposed to do, but in a bad way. And that's exactly what, so we kind of also show that this is exactly what you need to protect against these types of tampering attacks, right? So to make sure that if you tamper with the device in this sense of tampering with the code word, you won't get a value that's somehow useful, lets you break something that you couldn't do before.
Codes or anything.
Yeah, exactly. You can't use linear codes. Everything like that is off limits. Yeah. Because, well, it depends, again, what types of attacks. But if you consider, let's say, even the simple family of functions where you can add a known offset, you can do linear codes. Yeah. And so one thing we show is actually that non-malleable codes exist for every small enough family of functions. So if you choose any kind of family of functions to begin with, as long as there are some sufficient number of things you can't do, so the family isn't like the family of all functions mapping code words to code words. It's at least asymptotically smaller than that. You can come up with a non-malleable code that protects against this family of tampering. But unfortunately, again, this is non-constructed. It's kind of necessarily non-constructed because we say that even for all polynomial time things, we have non-malleable codes. But of course, there's kind of always an attack that just, the function of the code word actually decodes it, changes the last bit of the message and then re-encodes it, right? So there's always a malleability attack that you could potentially do. So then we also give some constructions for concrete examples. So one of the examples is exactly this, where you can tamper any number of bits of the code word you want, but for each bit you do it independently. So for the first bit you say, okay, I want to flip this bit. For the second bit, you can flip bits, or you can also kind of like set them to be to be a constant. So you can say the second bit I want to set it to 0. So you can completely override the so it includes like attacks where you completely override the code word with whatever you choose. It includes like adding known offsets, things like that. And so for that we have actually a constructive version. But of course there's a lot of open questions like how to do this for constructively for more general families. And that'd be really interesting. And all kinds of questions are not known, like what's the optimal rates, things that like coding theorists would like, generally ask about kind of coding questions. We don't know about this. Okay, so that's it actually. I wanted to just quickly summarize. So there's really many scenarios where the traditional view of how secret keys are generated, stored, and used does not hold. So you have things like leakage or password and biometrics. And I think there's a lot of opportunities here where better theory can lead to better security practice. I think there's a lot of good open questions left here. That's it. Thank you.
Any questions?
Do you expect any of these theoretical results to be actually applicable?
Probably not yet. So, but I think eventually, people are starting to develop general techniques. I think they will probably be, at least in some very modified way, useful for actual practical constructions later. I think that's how it usually works in crypto.
How about the huge key scenario? So does that sound like a reasonable
That's
possibility?
something that you could think of. There's a big drawback that I didn't mention, so I'll mention it now, which is if the virus is actually, let's say you're like using this key to log into your bank account, right? So then the problem is if you have a virus on your computer, maybe if it's active, it can just like use your computer itself to log into your bank account and do all kinds of bad things from your own computer. And there's kind of no way to prevent that. So what we prevent is, like, if the virus is active for a while and tries to upload something, or upload something to a remote attacker, then the remote attacker won't be able to log into your bank account. And or if it's like you've logged in a couple of times and done some things, and the virus is active later, then even if the attacker kind of saw this communication, they won't see what happened. It'll stay private. But we can't kind of prevent. So I think the reason people might not like this is they'll always think, oh, the virus will just do all the bad things it wants to do while it's on the computer itself. But in some sense, maybe those attacks are more sophisticated, harder to implement. So I think this might be reasonable in some cases.
For all your results are information theoretic, right?
No, just the first thing.
The first one.
Yeah.
Have you thought of doing non-malleable extractors in a computational sense, which might be enough for the type of applications?
Yeah, that's a good question. I didn't really think about it. I guess the point is that if you care about weak keys and things like that in a computational sense, we have kind of different set of tools that can do the same thing. So you wouldn't necessarily have to take this approach with non-malleable extractors. There's just kind of really different ways of doing it that we know of. Like, for example, these public key encryption schemes that are secure with weak keys already kind of solve the problem in a computational sense. So it's not clear exactly. I think if you were thinking from a computational sense, you might probably want to take a completely different approach, but maybe that you could think about like non-malleable extractors from a computational sense.
So in a lot of areas of cryptography, it's much easier to come up with a system that probably does work than one that actually provably works. Do you think in these cases that some of the complexity is necessary to work at all? Or is part of the complexity in giving actual proofs? And do you think that simpler systems might work in practice?
Yeah, great question. So I think it depends on some of the areas. So like for just designing public key encryption schemes that are secure with some partial leakage, but not continual leakage, I think pretty much any encryption scheme will be secure, at least in some sense, with some small partial leakage, because so there it's I think it's mostly a question of proofs. Like I think Al-Gamal would probably be secure, like the standard encryption scheme. For continual leakage, I just don't know too much about. I just have no idea in some sense. I have no idea how to do the updates without. I don't see any natural schemes for doing this that are much easier than what we ended up doing. So I think it really depends on the area.
So in a sense, this whole idea of having a secret key that's evolving doesn't seem to be a very natural notion, so, right?
Yeah.
I don't know of a
especially
off-the-shelf solution for this.
Yeah. For symmetric key crypto, people think of that because there it doesn't have to remain consistent with anything. But for public key cryptography, it really is very unnatural.
And I don't think there are any constructions that are not provably secure. There are just no constructions.
Yeah, exactly. I don't know anything.
Only that exist have already a proof of security. So there's no even heuristics that are.
It's not like I can't think of any way to simplify the construction that I would conjecture would be secure, but just can't prove it. Yeah.
So any more questions? Okay.
Thank you.